Okay, so it's my pleasure today to introduce Donsub. He's our speaker for this week's 1W-Minds seminar. Don is an assistant professor at the Washington University in St. Louis in the math department. This semester, he's visiting the University of Washington in Seattle. And today, he'll tell us about low-rank neurorepresentation of hyperbolic conservation laws. So please go ahead.
Hey, thanks, Waylin, for the introduction and the invitation. Thanks, everyone, for coming. So I'm going to talk about a type of a neural network called the low-rank neural representation and talk about its relation with hyperbolic conservation laws. So before I forget, this is joint work with collaborators, Woojin Cho, who's a graduate student at Yonsei University, Kookjin Lee, who is at Arizona State, Noseong Park at KAIST in Korea, and Gerrit Welper at University of Central Florida. And I've consulted Randy Lebec, my PhD advisor, about the conservation laws, of which he's a well-known expert. Okay, so here is the outline of the talk. So I'm going to first introduce what low-rank neural representation is. And I'm going to talk about some theoretical work relating how a learner approximation to entropy solutions to conservation laws, which can involve shocks and rarefactions, how it could be a low-dimensional approximation. So up to this point, it'll all be pretty much theoretical. But I will next talk about how there is a simple and straightforward meta-learning strategy, meta-learning framework that you can use for training these learners on solution data. So purely from data, you could train these learners. And I'll talk about how these learners have these built-in structure that allows you to construct a compressed version that we call fast learners, and how that leads to a faster backpropagation, that which we call sparse physics-informed backpropagation, but it's really just a faster approximate backpropagation for these types of neural networks. Okay, and please feel free to interrupt me at any point if you have questions. Okay, so just to set the setting, I'm going to introduce some notations for feed-forward neural networks. So a feed-forward neural network for given depths and widths, which are some dimensions that define the space of matrices and vectors. Given those, a feed-forward neural network is just a mapping that takes an input vector to the output vector. And in between, it applies an alternating concatenation, alternating compositions of affine maps and nonlinearities. These affine maps are parametrized by these weight matrices and these bias vectors. And so given vector z, it just multiplies the matrix and adds the vector. And these WLs and BLs for each layer is going to be the parameters of the feed-forward neural network. A sigma is a nonlinear activation. For example, the rectified linear unit, which just zeroes out negative entries of the vector, or for example, the tan h function. I'm going to, if I forget, during the theoretical portion, I'm going to focus on the ReLU. And in our computations, we actually end up using the tan h. And here, you apply the affine mapping, then the nonlinearity, and then affine mapping and the nonlinearity. And here the SO dot is meant to represent the entry-wise application of the scalar function, these scalar nonlinearities. Okay. So if you collect, the space of all the weights and biases, so this WL is just a space of matrices of the right dimension for each layer. This is just a space of vectors. If you collect them all as tuples in a Cartesian product, then we can say that this W, this B, just a collection of these a space of matrices and vectors. They define what we usually call an architecture, so to define the dimensions of these affine mappings. So if you sample a tuple of matrices, weight matrices for each layer and biases, and if you fix them, that is an instance of a feed-forward network, and that determines your function, which we say H, which is the feed-forward neural network. Okay, so in our setting, it's important to mention that our inputs will be spatial temporal, so they won't be a huge dimensional input. So for example, in many applications using neural networks, maybe more dominant applications of the neural networks, the input X is the pixelized image, which can have lots of pixels. You have a 256 by 256 image, then that's a lot of dimensions. Usually this X is taken to be high dimensional. But in computer vision, these neural networks are also used to represent continuous functions. And these functions have spatial temporal inputs. So maybe your spatial coordinates and maybe velocity fields and maybe the time. So let's say our input is at most 10 dimensional. So it's a relatively low dimensional setting when it comes to the dimension of the input. So in this case, people refer to these as an implicit neural representation rather than just a generic neural network, just to make the distinction. But of course, the underlying construction is often the same. Okay, so let me introduce what learners are. So we'll fix the architecture. So the dimensions of the weight matrices and the biases are now fixed. And we're going to focus on a certain parametrized family of weights and biases. So rather than allowing these W's and B's to be arbitrary, we're going to make them dependent on some external parameter S. And learners are when we enforce these WSs and BSs to belong to a small dimensional, in some sense, a small dimensional linear subspaces W hat and B hat. So these are parametrized by S, and they belong to this W hat, which is a lot smaller in some sense than the arbitrary space of any matrix. Rather than being any matrix, they're going to have some dimension related to them, and that maximal dimension is going to be across layers is going to be set to be a small number R. Hence the term low rank. So the low rank neural representation, rather than being a single neural network, is going to be a family of INRs. So family of implicit neural representations. And they're going to have this implicit dependence on S. Okay, so let me briefly mention, what do I mean by the dimension of this WL hat? So throughout, it's simplest to think about them as, so you have a family of matrices now, not just a single one, but one that depends on this parameter S. So for that set of matrices, I would like their shared column space to have to define the dimension of this. So the dimension of this WL hat, which is a set of matrices, we're going to say that the column space as a collection of matrices are going to be at most R. And we do also allow more complicated definitions for the dimension. For example, we say if it's block diagonal, we take each of these blocks and define dimensions for them, just to allow some Hadamard and Kronecker products. But I will not get into the details here. These are, easy to. These are to make the theory a little easier in our construction. But for now, we'll focus on this definition. And if you stick to that definition, it's actually easier to kind of give an explicit factorization of these weight matrices. So a simplified version is to take these weight matrices and consider to force them to have the same column space over all parameters. We say, okay, we factorize them in an SVD like factorization, and we say that the ULs, which are in the SVD factorization, we would refer to as the left singular vectors. We would sort of fix them to be independent of this parameter S. And also the right singular vectors, we would fix them. That way you have a shared column space. And we say only maybe the diagonal part depends on this external parameter S. So now that we have this factorization, we refer to these U and V's. Specifically, we refer to them as basis parameters, alluding to the fact that they're going to be fixed across all S parameters S. And we say this B is also going to be fixed and independent of S for the bias parameters across different layers. We call these bias parameters. And we say this S, which parameterizes our matrices, we're going to call them coefficient parameters. Sorry for all the new terminology, but I do think it makes it easier. So again, assuming spatial temporal inputs, this now is INR. Instead of having W and B, which were weights and biases, that parameterize them, we just have a slightly different parameterization in this factored form. So U, V, and B are the basis and bias parameters, and then S is the coefficient parameters. And this S appears as in the diagonals of this factor matrix form. So the idea is that we're going to learn the basis and bias parameters first. So U, V, and B, which form the left and right singular vectors, well, left and right singular vector-like matrices in each of the factorizations. And then we're going to fix them as U star, V star, and B star. And once these are learned and fixed, now our INR really only depends on the coefficient parameters S. And of course, since these are only the diagonal entries of the sigmas, you only have a very few of them, rather than having a dense matrix W, which could have lots of parameters. Now U and V are fixed, and if R is small, then S across different layers, you have S R times L coefficients. The number of coefficients is not very big. And in our setting, we're also going to set the layer to be a small number, L is equal to 5, as opposed to many applications where you have very deep neural networks over 100 layers or so on. And we will make the argument why L equal to 5 is reasonable in our applications. So finally, learner of rank R is just a family of neural networks of this form. And then we allow this S to vary. For example, we allow them to be positive. We set them to be arbitrary positive numbers in analogy to the SVD like factorization here. The SVD, this diagonal entries are non-negative. Okay, so that is a learner. So just to give you a visual example, let's say we consider a 2-layer example. Let's say the rank is 3, and the input dimension is 2, and the output is scalar. In that case, you have a weight matrix that, so it's still a neural network, so you can write it as this shallow neural network form. However, in the weight matrices here, it has this SVD-like factorization. And this block, which is the UL, is considered fixed and independent of the coefficient parameters S. This V is also fixed. And it's rank 3, so you have 3 of these coefficient parameters. So now this neural network is parameterized with, 3 coefficients for this weight matrix. And there's 3 parameters that parameterize this W2. And of course, you could also factorize the biases too, and that's what we do for the theory work. But of course, that's a straightforward extension of this idea of parameterizing your weights and biases and make them belong to a low-dimensional space. Okay. So this was motivated by seeking a low-dimensional representations of parametrized PDEs. So let me quickly make a connections to parametrized PDEs. Suppose you're interested in solving a parametrized partial differential equations, which are just abstractly given by these 2 equations. So here n is some differential operator that could depend on the physical parameter mu. So you'd like to solve n of u is equal to 0. And maybe B is a boundary operator, which also depends on the physical parameter. And we want to also solve BU is equal to 0. And what we are trying to do with the learner is to say that, okay, maybe we'd like a learner to represent our solution U. And maybe there is some part of the functional form of U of the learner that is shared across all the solutions of the PPD. So in this SVD-like factorization, we are kind of saying that maybe only this sigma is dependent on this coefficient parameter S, and maybe that coefficient is the only thing that depends on the physical parameter mu. So we say that mu is the only, S is the only parameter in this learner parametrization that depends on the physical parameter mu. And these ULs and VLs, the basis parameters are independent of the physical parameter mu. So this means that the dependence of the physical parameter is particularly simple for this learner parametrization. So the idea is to approximate your solution, U of mu. Sorry, this S shouldn't be there. It's a U of mu. You would like to approximate it by a learner who, again, is parameterized by a small number of coefficient parameters. And maybe there's a relation between S and mu, but not with the rest of the parameters. And these are going to be fixed throughout. And they will contain information that's global to the solution across the PPD. Okay, so let me say something about how this construction is related to the entropy solution to scalar conservation laws. So as you might have noticed, this PPD parametrizing the solution to PPD so that you can exploit low dimensionality is, of course, not a new idea. In the field of model reduction, this is actually one of the key goals. And let me give you a very brief overview of how reduced order modeling works, or model reduction procedures work. So in an intrusive model reduction, you do something quite similar to what I mentioned before in the previous slide. You take a parameterized PDE. So mu is, again, a physical parameter, and U is the solution to your PPDE, and it depends on this mu. In classical model reduction, what you do is you'd like to represent this U mu by a linear combination of a few basis functions, and these are referred to as reduced basis functions. So you say that U hat of mu is a low dimensional representation of U, and they're always represented by this a linear combination of a few reduced basis functions. And if you can figure out the coefficients that correspond to the best coefficient that fits the requirements of your PDE, then you have an approximation to your solution, and you have only R. R is the number of coefficients you have, so it's a very low dimensional approximation. So this part I call the sort of the encoding of your solution. You encode it in these few coefficient values. And the benefit of the reduced basis representation is that you can often find a reduced system that minimizes some residual of your Galerkin system, for example, to solve the PDE. And this solve is fast. And in the best scenarios, of course, for some PDEs this is difficult to derive. But in the best case scenario, you can solve the same PPDE projected to these reduced basis space, and you can do a quick solve to find these coefficients. And the complexity to do that scales really only polynomially on the small dimension R. So you can actually solve the PPDE really quickly. So you can do a fast solve. And then sometimes you're interested in some quantity of interest, which is some bounded linear functional that applies to your solution. So and you can find this very quickly too. So this framework, where you do this offline work to encode your solution first, and during the online stage, doing a fast solve and computing the quantity of interest. This strategy overall is called nowadays called an intrusive method. Of course, there's a data-driven method, non-intrusive methods, which directly go for the mapping that maps from the physical parameter to the value of the linear functional directly. So don't worry about the PDE. If you have samples of this mapping, you can try to fit a regression map, for example, using neural networks, and neglect the PDE and then go for the quantity of interest map directly. Okay, so the reduced spaces methods, they kind of rely on the assumption that you do have a uniformly accurate approximation of the solutions to the PDE in the form of reduced spaces representation. So you're kind of assuming that first the solution in your PPD, you have a uniformly accurate U hat for a fixed reduced spaces size, these size which are the reduced spaces. So such a reduced spaces must exist for you to even attempt to represent, to construct a reduced model. And whether you can do this is described by the Kolmogorov N-width. So the Kolmogorov N-width, sorry, I used R here. Usually N goes here, but I've been using R consistently. So the Kolmogorov N-width is defined as it's defined as the best uniform approximation error for your solution manifold if you can find the best reduced basis functions of dimension n, in this case, dimension r. And so if the Kolmogorov N-width decays quickly, exponentially, it means that you can choose the dimension of your reduced basis to scale with the log of epsilon, where epsilon is the uniform error threshold. And since as epsilon goes to 0, R grows slowly, it means that you can get away with a very efficient reduced basis representation. If you compare this with the standard numerical methods, like finite element methods or finite volume methods and so on, to have a uniform approximation error there, as in the form of when you represent it as a linear combination, for example, finite element basis functions, and let's say you have a capital N of these basis functions, which is usually large for practical problems, then typically for the error threshold, N would scale something like the error to the -1/gamma, where gamma is the convergence order of your method. The spatial dimension is missing here, for example, just to say that we're going to focus on one-dimensional problems, just to illustrate the difference in the scaling. So here, N scales with the delta to the -1/gamma, which grows a lot more rapidly than log of epsilon, for example. So this is the key requirement for reduced basis methods to be successful. And of course, for hyperbolic problems where sharp features are moving in your domain, you have a slow decay in the Kolmogorov N-width. So here we're going to view time as the parameter. And so there's many solution manifolds that have a slow decaying Kolmogorov N-width. And even the simplest problems, for example, this advection equation where the jump comes in and travels to the right, you can show that the N-width has a lower bound that scales like this, R to the -1/2, and this scaling looks much more like the finite element degree of freedom scaling with respect to the required error, as opposed to something like log of epsilon. So the degree of freedom you need for uniform accuracy in the reduced basis setting would have to be very big, just as big in some sense as a finite element method. So reduced basis methods are not very successful in accurately representing this moving front. If you have a little more regularity, for example, rather than having a jump, if there's a jump in the derivative or the second derivative, it does decay a little faster, but still it scales much more like the standard numerical methods rather than something like log of epsilon. However, one quickly notices that for the advection equation is just one profile that is traveling. So you have some initial condition that's being translated to the right. So one thing to notice is that there is some low dimensionality in this inner function, this x minus t, the translation. So if you write x minus t as if you view it as a linear combination of two spatial functions, for example, the identity function and the constant function, then this x minus t is just a linear combination of two functions. So there is some low dimensionality built into this compositional form. So this idea has been exploited and studied a lot in recent model reduction literature. And one approach is to extend a reduced basis method is to introduce a transported subspace. So rather than sticking with the linear combination functions, let's say you have two basis functions. So these phi i's and psi i's. And let's say you have these two set of coefficients. And in 1D, what you could do is you could do this, you could compose two of these objects. So let's say you take F and G, which are each belonging to some reduced basis representation with basis functions psi's and phi's, and you can compose them together. There is an inverse here because in method of characteristics, you trace back where your characteristic curve is emanating from. So there is this inverse map. So if you have a collection of these functions, then they represent a more efficient travel. They give you a more efficient traveling wave representation compared to the standard reduced basis methods. And moreover, you can show that in some simple cases, the cost for updating the bases, that is to plug them into a PD and actually minimize the residual in some sense, you still preserve the ability to do that with a polynomial in our operations. So it is fast solvable just like the reduced basis methods. So for example, if you have these two basis functions and if you take linear combinations of them, then you get these types of functions. If you take phi1 and phi2, this phi1 is the identity. If you take linear combinations of those, you get these types of functions. So if you take each of these and compose with F, then you get this traveling wave motion. So you're able to represent translating and maybe slightly modulating traveling wave profiles that more efficiently than just taking linear combinations of reduced basis functions. Okay, so the two examples here and here, you can kind of reformulate them so that you can show that they also have this low dimensional representation. Okay, for the interest of time, let me just skip this slide. Let me just quickly say that, okay, that is not the end of the story. Even if you could find nonlinear extensions of reduced basis methods that could encode and do this fast solves, there is also this additional problem of computing the quantity of interest map. So in the linear setting, linear reduced models, if you could encode and do fast solves, then your quantity of interest map, it's trivial to calculate them. However, in the nonlinear setting, even if you are able to do fast solve, there is still this issue of computing the quantity of interest map. And we have some results saying that in the theoretical worst case, there is actually no tractable strategy to solve them in a very high dimensional transport problems. However, we believe that the current moment achieving this fast solve is the first problem we have to handle. And many of the methods that were introduced have a good encoding, but they do not allow fast solves. And I also want to sort of mention that even if you go the data-driven route and you use the deep learning models, they often suffer from input instabilities called adversarial examples. So you come across a different set of challenges there too. Okay, so let me try to, I introduced learners and I've said something about transport subspaces. Let me try to convince you that learners are actually just generalization of transported subspaces. So as before, let's choose the outer function f in the transported subspace to be piecewise constant. And it turns out that choosing these to be piecewise constant is very useful. So if you take the transported subspace f composed of G inverse, and if f was piecewise constant, then and you apply the G inverse map, then since this is this rho is a jump function, it's a Heaviside function. So you represent f since it's piecewise constant as a linear combination of jump functions placed at the grid point x sub I. Then this G inverse, which x on x, it really this jump function really only cares about whether x is bigger than x sub I or it's less than x sub I, right? So this G inverse is as long as it's a invertible monotone nice function, you can move this to this term. Because this is invertible, you're really only comparing G inverse of x with x sub I. You can move this. You can remove this inverse, and an equivalent representation is given on the right, and you apply G to x sub I. So I think this is, of course, intuitively well known in the numerical analysis community. So if you want to deform the domain, for example, rather than worrying about how to apply this inverse map, what you could do is you can move the grid point x sub I to G of x sub I, and then you have a representation of your updated solution where you deform the domain of your 1D domain without having to worry about calculating the G inverse. Of course, it's implicitly, you have to do some work later on, but this seemed this seems like a well-known strategy. However, this if G was not piecewise constant, then of course G inverse affects everywhere, not just at the grid points. So I think there is something special about using f, enforcing that f is piecewise constant. And we were really constantly looking for a reference in the literature that explicitly says this, but we couldn't find it. So we say that this is we call this an inverse bias trick. Because here the inverse has vanished. And if you squint a little bit, it looks like this term. It looks like the bias. And by that, I mean, if you look at this form of f composed of G inverse, it kind of looks like a shallow neural network. And this term, G applied to x sub I, it looks like you're applying it to the bias term in the first composition. And furthermore, in transported subspaces, we assumed there were two basis representations for f and g, which would mean that if f belonged to a low-dimensional space, these betas would belong to a low-dimensional space, which would correspond to these weights belong to a low-dimensional space. And if g was low-dimensional, then this b sub I would also belong to a low-dimensional linear subspace. So it's you arrive at something very close to low rank neural representation where you say, okay, we have a neural network, but we restrict these individual weights to belong to low dimensional subspace. Indicates just a simple low dimensional linear subspace. Okay, so that's how they are connected. And of course, you can make the argument that whenever you have any transported subspace of rank R, so each of the dimensions of both the subspace for F and G, if they are both dimension R, then you just need one more rank learner with a learner with two layers that can uniformly well approximate that transported subspace. And there's a nice mapping between the coefficients alphas and beta, which parameterize the transported subspace, and essentially the coefficient parameters of the learner. I called this S before, but in this theory work we use gamma and theta because we I think we use S for something else. I think S is the shock speed in that paper. So sorry about that. But so these are the coefficient parameters of the learner. And it's not really hard to see. So these objects, where you learn in the learner, you set some rank for these weight matrices, is essentially equivalent to F composed with the G inverse, which is in this form. Okay, so immediately it follows that for scalar conservation laws, ut plus f of u x is equal to 0, where f is smooth and strongly convex flux function. The classical solution to this has a transport, not only a nice transport subspace representation, but also has a nice learner representation, because learner and transport subspaces are closely related to each other. So a learner with rank 3 and 2 layers can approximate the classical solution uniformly well. So this is a technical statement, but of course, again, intuitively speaking, it's not very difficult to see, because the classical solution itself, using classical characteristics, is just the initial condition composed with X inverse, where here this inverse is applied to the spatial variable. And the characteristics are straight lines for this problem. So you can write it as a linear combination of two functions, namely the identity plus the f prime composed with u0. So t, which is time, is the coefficient. And so this looks like a linear combination of two functions, just very similar to just a advection equation where things are translating to the right. Of course, the entropy solution to the same problem is the interesting solution. The classical solutions are very limited. They form a very small subclass of entropy solutions. So for example, if you consider the Burger's equation, which is the archetypical problem in that class of conservation laws. If you have an initial condition that looks like this, maybe some sinusoidal waves and some jumps, then if you have a negative gradient, a decreasing portion, that will eventually form into a shock at different times. The shocks will merge together. You'll get rarefaction waves if you have an entropy violating shock. And the rarefaction waves will interact with the shock and affect the speed at which it propagates. So all of this is much more complicated than just translating profiles. So the question, of course, is then, is there a sort of a generalization of this low-rank structure that we observed before, when the characteristics were nice, to this more general case, the entropy solution? And as I was slowly alluding to, the answer is yes. And we believe that the low-dimensional structure is given exactly in the form of learners. So there is a low-rank neural representation with rank equal to 2 and L equal to 5 that can approximate the entropy solution with arbitrary initial condition uniformly well. So if you give me one initial condition and the time-dependent entropy solution, I can find a learner with rank equal to 2 and 5 layers that can approximate the solution uniformly well. So in a way, this increasing the number of layers in the learner gives you a lot more flexibility in handling shock interactions and rarefactions and so on. So this is the technical statement. The important thing here is that our initial condition, we're really assuming it to be a bounded variation and compact support. So there is really no interaction with the boundary. And another thing is that the coefficient parameters are going to have an affine dependence on t. So let me just dwell on that a little bit. So in the classical case, we know that this coefficient t multiplying the spatial function f prime composed with u0 is essentially, it's an identity function of t. So it's a very regular function. So although the conservation laws, the characteristic is changing over space, the dependence on the time is actually quite regular and simple. That property is actually maintained in our learner approximation. So the coefficients gamma and theta t, which correspond analogously to these diagonal s's that we saw before, those are going to be affine functions of t. So the dimension of the learner, the r comma l, 2 equal 2 comma 5, is independent of the complexity of the shock topology. So you can have as many shocks as you like, as complicated as you like. However, this dimension is not affected by that. And again, the time evolution is regular, although there are spatial discontinuities. So a lot of the information about the shock interaction has moved into the fixed portion of learner, these basis parameters, and the time dependence is particularly simple. So in some ways, it has a lot of themes built into it that goes back to the 80s. There are many, of course, there's many papers, many different methods that were studied for solving the scalar conservation laws, and methods like large time step methods or average multi-solution solutions, which were explored. Then there are some similar flavors that inspired this work. Okay, so to give you sort of a short overview of how this result comes about, just as the translating profile, or the D'Alembert solution to the advection equation has a particularly simple form if you add more compositions, the same is true for the entropy solutions. You have to do some work to tease out this form, but what we were able to do in our work was this: you can take your old, you can modify your initial condition and your characteristics to mold the entropy solution into a new representation of this form. This plus is the left inverse. These roughly correspond to the classical characteristics. And these, this is a jump function, and these contain the information of when the characteristic merges into the shocks. So these basis functions, so to speak, are they're related to physical quantities of the solution. Okay, and so we say that this is in a low rank form because, for example, if you look at the second layer, it is a linear combination of three functions, so phi1 and phi2 and phi3. And the coefficients are, 1 and t and 1. And these are values that were coming in from the previous layer. And for example, if you observe this representation, it's also rank 2 because it's taking a linear combination of two functions, var phi1 and var phi2. Okay. So that's the theoretical portion. Let me, during the remaining time, try to convince you that this is also trainable in what's called a meta-learning framework. Okay, so before I mentioned that, okay, maybe the bias and the basis and bias parameters are learned first, and fixed. So U star and V star, B star, which contain global information about your solution, is learned and fixed. And then after this phase, you can actually do a data-driven prediction of the for example, if you're interested in the parametrized PDE, then you can give a data-driven approximation at the end of this so-called meta-learning phase after this has learned. However, in model reduction, we had this fast solve stage. So ideally, we'd like to plug in learners with these parameters fixed, and depends on the low dimensional parameter. You'd like to put it into the PDE and minimize the residual so that you actually find a good approximation of S sub mu using the PDE itself. So you're saying, we're kind of saying that we are using the coefficient parameters to solve the PPDE through this ansatz, the learner ansatz. And I think I'm going too slowly, so I'll probably run out of time before I get to the details. But this is when the faster backpropagation, which is the computation of the derivatives you need for this fine-tuning phase, we can make it scale with the complexity that is polynomial in R, and doesn't depend on the large degree of freedom like the finite element methods. Okay, So what is this meta learning framework? It is particularly simple. So we do not really know the relation between, for example, if you're solving the PPDE, there was a physical parameter mu. And we assume that we have the ability to solve this PDE using a standard numerical method. But we do not know the relation between mu and these diagonal coefficient parameters S. So this is just a three-layer learner that I introduced before. And there is these diagonal coefficients that's supposed to depend on the parameter mu. And there is these basis parameters U and V that are independent of it. So since we do not know the relation between mu and S, the straightforward approach is to construct a neural network and fit it to the data. And this seemed too simple of an idea, but my collaborators, they have convinced me that it works, this simple approach, and it's called the meta learning framework. So this hyper network is just a standard feed-forward neural network. And it doesn't have to be very big if your parameter space mu is also not too big. And we also, if we can reduce the dimension of these coefficient parameters, then the input and outputs are not very big. So this neural network doesn't have to be very big. So you assume that this hyper network is mapping from your physical parameter space to the space of coefficient parameters. And now you have this meta network, which is a gigantic network that houses the learner. It also it houses the INR that has you have to learn the basis parameters, the bias parameters, and the hypernetwork all at the same time. But you learn it from solution data from standard numerical methods. So you construct a misfit, and since I'm running out of time, let me just mention that there's to promote the low rankness in each of the layers, we introduce not only this orthogonal regulation, which is a soft constraint forcing the basis parameters to be orthogonal. We introduced some sparsity promoting regularization to enforce that the singular values are sparse as much as possible. The coefficients parameters, there's only a few that you really use. And then you construct this meta learning phase loss, which is a data misfit plus these regularization terms, the orthogonality enforced on the basis parameters, and the sparsity enforced on the coefficient parameters. And let me show you an example. If I could switch to another window. Okay, so in conservation laws, this is a compressible orders equation example. There is a classical problem called the Woodward-Colella shock problem, where these are three output variables of the system. There's the density, velocity, and energy. And so there are two shocks that collide with each other. And so these dashed lines are where we gave this a meta learning problem, the solution data coming from a finite volume method, the ClawPack software package. And we've trained learner. And on the right, we're showing the evolution of the coefficient parameters. So in most of the layers, the maximum rank for this learner is, I guess, it's less than 150. So this blue learner representation is roughly 150 dimensional object, which is I guess I'm arguing that it's not too big to represent this shock collision problem, which is very complicated. So it's only really seen the solution at these dashed lines. So I've given it solution snapshots at very rough time intervals. But after it's trained, it is able to sort of move this shock from left to right and right to left pretty gracefully. So it looks pretty physical. And it also is able to sort of represent this complicated shock interaction behavior in a physically plausible way. Let me wait for the movie to play out. So it seems that the learner is able to learn through this meta-learning method, the low-dimensional structure in complicated shock interactions. So we've compared the situation with the standard methods like convolutional neural networks. So we took the same solution data, and then we learned a convolutional autoencoder, and we tried to interpolate what goes in between these course-timed solution data. And what it does is, even if you ignore the wiggles, between the solution at two different times, this solid line is moving to the right. It's a part of the Woodward-Colella shock problem. What the convolutional autoencoder does when you try to interpolate is it tries to fill in this gap. It kind of horizontally fills in this gap. So you see these horizontal steps filling in, and then it removes this portion down. Whereas if you use learner, it tries to shift things from left to right. So somehow this learner constraint, I think, is forcing things to move rather than to have this vertical motion of horizontal steps on the left slide. We applied this to, for example, the 2D Burgers equation with periodic boundary. So there is this blob in this problem. There's a shock front that propagates, and as it hits the right corner, it comes around in the left corner because it's a periodic boundary condition. And then soon this shock interacts with the rarefaction fan, which affects the speed. So it's a fairly complicated interaction. And if you had to explicitly find what is the transported subspace representation for such things, it is not straightforward because there's shocks forming and characteristics are merging and so on. However, if you train a learner, you seem to learn roughly an 80-dimensional representation of it. On this second plot is the slice of the solution at this dash line. And what's also interesting is since learners are neural networks, they can be evaluated outside of the physical domain. So this dashed box is the physical domain, which is equivalent to this plot over here. You can plot what the learner is doing outside of the physical domain where it has not really seen any data. And of course, the data is not available because it's the solution. You're kind of evaluating something outside the computational domain. And the way that it constructs this periodic incoming data is it prepares these fictitious looking blobs and then prepares them just the right way that it kind of looks like the solution as it enters the domain. So it seems like it is extrapolating something in space. Of course, these are not physical. These are not, of course, a periodic extension of the initial condition at all. However, the learner seems to learn something that is actually at least traveling and is not suddenly appearing or disappearing. Which I think was interesting. Of course, this is also not physical, but it seems the solution is gracefully leaving the domain, which I think is an interesting phenomenon. And I think it is because we have enforced this low rankness, and it has to do. It's enforcing it to learn something that is moving gracefully rather than abruptly changing. Here is another example, the acoustics equations with periodic boundary conditions. And again, it learns roughly 130 or so dimensional object. Again, there's a periodic boundary condition, so this wave comes back in and it interacts. And of course, there is no, in this case, there is actually no nice characteristic representation because it's a 2D problem. Although there is a classical object, the Lax-Phillips translation representation, which I think is maybe theoretically the closest thing. So it is able to learn the low dimensional structure in this case as well. Okay, since I have gone too slowly, let me just finish by saying just a couple things about the backpropagation. So because of the low rank structure, you can compress between the two contiguous layers because these are coming from a low rank linear combination of low rank objects. You can compress this into a smaller network and do a backpropagation on that. So it accelerates your backpropagation to depend really on the reduced degrees of freedom, which is roughly the R, that the rank that I've mentioned. And we're hoping that we could be using this, we could use this to solve PDs that have shocks and rarefactions. I would just let me just finish by mentioning that we have used the PINS framework to do some of this. So in this paper, fast learner and sparse physics informed backpropagation, we were able to solve very simple PDs very quickly using this. So it seems promising. And this paper contains the theoretical work I mentioned in the beginning. And this is the paper where we introduced the meta-learning framework for learning these low-rank neural representations. So I think I have said enough, and so I think I'll stop here.